A meter stick is balanced on a knife edge at its center. When two coins each of mass 5 gram are put one on top of the other at the 12.0 centimeter mark, this is found to be balanced at 45.0 centimeter. What is the mass of the meter stick? Now, to understand the situation described in the problem, let's draw a diagram. It will be like this. In the diagram, C is the point where the two coins of total mass small m equals 10 gram are placed. B is the point which is the center of gravity of the scale from where the total mass capital M of the meter scale acts. Now we can write down various distances from figure. Clearly AB equals 50 centimeter or 50.0 centimeter. AD is the new balancing point and it is equal to 45.0 centimeter. Clearly AC is the point at a distance of 0.0 centimeter from the point A. So it is equal to 12.0 centimeter. Now CD equals AD minus AC. It is clearly equal to AD means 45.0 centimeter minus AC means 12.0 centimeter. So that's equal to 33.0 centimeter. Now DB equals AB minus AD equals 50.0 minus 45.0 equals 5.0 centimeter. Now taking moments about the point D, we can write the value of the anti-clockwise moment is mg into CD. mg into CD is the anti-clockwise moment. It is numerically equal to the clockwise moment, which is mg into dB. From this we get capital M, the mass of the meter scale, to be small m into CD divided by dB. This is equal to 10 into 33.0 divided by 5.0. This, when simplified, we get 66.0 gram. This is the mass of the meter scale. Okay. A solid sphere rolls down two different inclined planes of the same heights but different angles of inclination. A. Will it reach the bottom with the same speed in each case? B. Will it take longer to roll down one plane than the other? If so, which one and why? Now to understand the situation, let us draw two diagrams. The diagrams will be as shown. In both the cases, we see that the initial height of the sphere is h, or the initial energy given to the sphere is the potential energy mgh. Now, as it rolls down along the inclined plane and as it reaches the ground, this mgh is completely converted into the kinetic energy of translation and the kinetic energy of rotation. It is equal to half mv square plus half I omega square. This is equal to half mv square plus half into the moment of inertia of the sphere about its own diameter is 2 by 5 mr square. So that into omega square. So this is equal to half mv square plus 1 by 5 mv square. Why? The velocity or speed v is equal to r into omega. Now this is equal to, taking LCM and simplifying, we get as a 7 mv square by 10. From this we get v square as a 10 GH divided by 7, or V equals, this implies that V equals square root of 10 GH divided by 7. Thus we see that the speed with which the sphere reaches the ground is independent of the distance traveled by the sphere or the inclination of the inclined plane. So in both the cases, the sphere reaches the ground with the same speed v given by root of 10 gh by 7. Now let us solve the next case. Will it take longer to roll down one plane than the other? Here, this is a combined case of translatory motion and rotation motion. So, we can express the distance travelled as S equals the average speed u plus v by 2 into time. The initial speed u equals 0, therefore this is equal to v by 2 into t, or we can write t proportional to s. That means t proportional to s means h by sin theta, h divided by sin theta. So t1 by t2 means h by sin theta 1 divided by h by sin theta 2, or this is equal to sin theta 2 by sin theta 1. So clearly we see that from the diagram t2 greater than t1 because theta 1 greater than theta 2. So the sphere takes a longer time in the case of the incline of small angle of inclination. Okay. A hoop of radius 2 meter weighs 100 kilogram. It rolls along a horizontal floor so that its center of mass has a speed of 20 centimeter per second. How much work has to be done to stop it? Hoop means a ring. We can write the radius of the ring as r equals 2 meter. Then mass of the ring as m is equal to 100 kilogram. Then the speed of its center of mass, say v, equals 20 centimeter per second, or it is equal to 0.2 meter per second. Here, the work done in stopping the ring is equal to its initial kinetic energy minus final kinetic energy. Clearly, the final kinetic energy is equal to 0 as it comes to rest. Therefore, work done is equal to the sum of its initial kinetic energy of translation and kinetic energy of rotation. That means this is equal to half mv square plus half into I omega square. This is equal to half into mv square plus half into the moment of inertia of the hoop is clearly m square. So that into omega square. So that's equal to half mv square plus half m into r omega means v, or v square, because v is equal to r omega. This means mv square. So that's equal to m means 100 and v means 0.2. 100 into 0.2 whole square. This is equal to 4 joules. This is the work to be done in stopping the hoop. Okay. The oxygen molecule has a mass of 5.30 into 10 raised to minus 26 kilogram and a moment of inertia of 1.94 into 10 raised to minus 46 kilogram meter square about an axis through its center perpendicular to the lines joining the two atoms. Suppose the mean speed of such a molecule in a gas is 500 meter per second and that its kinetic energy of rotation is 2/3 of its kinetic energy of translation. Find the average angular velocity of the molecule. Now, in order to understand the situation, let us draw the diagram of the oxygen molecule. It will be like this. Now, the mass of the oxygen molecule can be written as m equals 5.30 into 10 raised to minus 26 kilogram. Moment of inertia I equals 1.94 into 10 raised to minus 46 kilogram meter square. Mean speed of the molecule is V is equal to 500 meter per second. Also it is given that its kinetic energy of rotation, that means K rotation, equals 2/3 of its kinetic energy of translation, that means 2/3 of KTR. We have to find the average angular velocity of the molecule, that means we have to find omega. We can transform this relation, kinetic energy of rotation equals 2/3 kinetic energy of translation, in this form. It is half into I omega square, that's kinetic energy of rotation, that's equal to 2/3 into kinetic energy of translation, means 2/3 into 1/2 mv square, that's equal to 1/3 mv square. Therefore, the angular velocity square omega square equals 2/3 mv square divided by I. Substituting the values, we get 2/3 into mass of the oxygen molecule is 5.30 into 10 raised to minus 26 into V square means 500 square divided by I is going to be 1.94 into 10 raised to minus 46. Simplifying this, we get 45.54 into 10 raised to 24. Therefore, omega is obtained to be 6.75 into 10 raised to 12. So much radians per second. Okay. A solid cylinder rolls up an inclined plane of angle of inclination 30 degree. At the bottom of the inclined plane, the center of mass of the cylinder has a speed of 5 meter per second. A. How far will the cylinder go up the plane? B. How long will it take to return to the bottom? Now, in order to understand the problem, let us draw a diagram. Now, let's do A part. In this case, as the solid cylinder rolls up, it has two types of energy. There is kinetic energy of rotation and kinetic energy of translation. So, the sum of the kinetic energy of rotation and kinetic energy of translation gets converted into the final potential energy when it reaches at the height h. So, we can write the kinetic energy of translation plus kinetic energy of rotation equals the final potential energy mgh. That means half mv square plus half into I omega square equals mgh. That is half mv square plus half into the moment of inertia of the cylinder about its own axis mr square by 2. So that into omega square equals mgh. Now this can be written as half mv square plus 1/4 m r omega means v, so 1/4 mv square, that's equal to mgh. So half mv square plus 1/4 mv square equals mgh because v is equal to r omega. That means 3/4 mv square equals mgh. Therefore, h equals 3 v square divided by 4g. Now we have to find the distances traveled by the solid cylinder. For that, we see that sin 30 equals h divided by s. Therefore, h is equal to s sin 30. So, we see that s we see that S into sin 30 equals 3v square divided by 4g, or S equals 3v square divided by 4g into sin 30 in the denominator. Now substituting the values, we get this as this is equal to 3 into 5 square divided by 4 into 9.8 into 1 by 2, or this will be equal to 75 divided by 19.6. This one calculated, we will get 3.83 meter. So this is the distance up to which the cylinder rolls up. Now let us do the second part, B part. How long will it take to return to the bottom? To solve this, we can consider the average velocity and express the displacement in terms of the average velocity. That means S equals u plus v by 2. This is the average velocity into time. This is equal to u means the initial velocity 5, v means the final velocity which is 0, divided by 2 into t. So from this we get t is equal to 2s divided by 5, or it is, so t is equal to 2 into 3.83 divided by 5. This is found to be 1.532. Now consider the downward motion. Then we can write the same relation, S equals u plus v by 2 into t. But here the initial velocity u is equal to 0 and the final velocity v is equal to 5. So 0 plus 5 by 2 is the average velocity into time. So again we get t as 1.532 seconds. Therefore, total time taken by the cylinder to return to the ground is given by t equals 1.532 plus 1.532 equals 3.064, or it is approximately equal to 3 seconds. Okay. As shown in figure 740, the two sides of a step ladder BA and CA are 1.6 meter long and hinged at A. A rope DE 0.5 meter is tied halfway up. A weight 40 kg is suspended from a point F 1.2 meter from B along the ladder BA. Assuming the floor to be frictionless and neglecting the weight of the ladder, find the tension in the rope and forces exerted by the floor on the ladder. Take small g equals 9.8 meter per second square. Hint: consider the equilibrium of each side of the ladder separately. In order to solve this problem, let us consider a diagram. This diagram shows the detailed structure of the forces acting on the system. In the figure, we can write various values. AB is going to be 1.6 meter. AD equals DB equals 0.8 meter. AF equals 0.4 meter. D equals the length of the rope. It is equal to 0.5 meter. Now from figure, triangle ADH is similar to triangle ABI. Therefore, we can write AD divided by AB equal to DH divided by BI. This is equal to AD means 0.8 divided by 1.6 equals DH means 0.5 by 2 or 0.25 divided by BI. From this we see that BI equals 2 into 0.25 or it is equal to 0.5 meter. Similarly, the same ratio is equal to AH divided by AI. Therefore, it is clear that AH equals AI divided by 2. But AI equals എന്തായിരിക്കും AI equals square root of AB square minus BI square equals square root of 1.6 square minus 0.5 square. This is equal to 1.52 or it is approximately 1.5 meter. Now let us take moments about A of various forces. Taking moments about A, we see that W into Ki. W into Ki is the anti-clockwise moment about A of the weight W equals 40 kg. Then plus the next anti-clockwise moment is that of the tension T. So T into AH. This is equal to the clockwise moment acting on the ladder AB is NB into BI. So that's equal to NB into BI. That's equation 1. Now W equals 40 into 9.8 equals 392 newtons. AH equals, we have seen that AH equals 1.5. H equals 1.5 divided by 2 or is equal to 0.75. BI, we have seen that BI equals 0.5 meter. KI, from figure it is clear that KI equals BI divided by 4 or it is equal to 0.5 divided by 4 or it is equal to 0.125 meter. Substitute these values in equation 1. Equation 1 becomes 1 implies that 392 into 0.125 plus T into 0.75 equals NB into BI means 0.5. Therefore, we can write this as 0.5 NB, 0.5 NB minus 0.75 T equals 392 into 0.125 or it is equal to 49. That is be equation 2. Now let us consider the equilibrium of the ladder AC. The anti-clockwise moment acting on the ladder about the point A is given by NC into IC. NC into IC, this is numerically equal to the clockwise moment of the tension T. That is T into AH. IC means 0.5. So 0.5 NC equals H means 0.75. 0.75 T or we can write 0.5 NC minus 0.75 T equals 0. This is third equation. Now subtracting 3 from 2. That means 2 minus 3 implies that 0.5 NB minus 0.5 NC equals 0.75. T gets cancelled and that's equal to 49. Or we see that NB minus NC equals 49 divided by 0.5 or it is 98. This is relation 4. Now the downward force is W and the total upward force is NB plus NC. So we can equate the magnitudes of the two forces acting the opposite direction. NB plus NC, sum of the upward forces. It is equal to the total downward force, that means W. Or we can write this is NB plus NC equals 392 This is relation 5. Now adding 4 and 5. 4 plus 5 gives that 2NB equals 490. Or we get NB as 245 newtons. Now relation 5 gives NC as 392 minus NB. That means 245, and that's equal to 147 newtons. Now the only quantity which we have to find is the tension acting along the string D. For that, let us consider equation 2. Then equation 2 becomes 0.5 NB minus 0.75 T equals 49. Therefore, 0.75 T equals 0.5 NB minus 49. Therefore, T equals 0.5 NB minus 49 divided by 0.75. This is equal to 0.5 into NB means 245 minus 49 divided by 0.75. This is found to be 98 newtons. So the tension is equal to 98 newtons. Okay. Now let us do the problem in a different method using vector algebra. For that, again we have to draw a figure. In this figure, we consider two straight lines, horizontal and perpendicular, intersecting at the point A as the system of coordinate axes. Now, with respect to this coordinate system, the vertex A has the value 0, 0, and the point B and C will be minus 0.5, minus 1.5, plus 0.5, minus 1.5 respectively. This is clear from our previous discussion. We have seen that DE equals 0.5 and a triangle ADE similar to triangle ABC. So we see that BC equals twice DE because AD is half of AB, and so this is equal to 1 meter, and thus we see that BG equals 0.5 meter. Therefore AG equals square root of AB square minus BG square equals root of 1.6 square minus 0.5 square, that's equal to 1.52 meter, or approximately it is 1.5 meter. Also we can write W vector equals W into minus J cap equals W means 40 kilogram, or 40 into 9.8 equals 392 newtons. So minus 392 into J cap. Also NB vector is the upward reaction force, and it is given by NB into J cap, while NC vector equals NC into J cap, and T1 vector equals T into I cap. It is acting towards right. So T2 vector equals T2 into minus I cap. Now for the equilibrium of the ladder AB, for ladder AB, the torque about A, that means tau A equals 0. That means AB vector cross NB vector plus AD vector cross T1 vector plus AF vector cross W vector equals 0. Let AB vector equals B vector. This is equal to minus 0.5 I cap minus 1.5 j cap. Also, it is clear that AD vector equals B vector by 2, while AF vector equals B vector divided by 4. Therefore, the above relation becomes B vector cross NB vector plus B vector by 2 cross T1 vector plus B vector by 4 cross W vector equals 0. Now, this can be written as a B vector cross within bracket NB into j cap plus T plus T I cap by 2 minus W j cap by 4 equals 0. That means minus 0.5 I cap minus 1.5 j cap cross NB minus W by 4 into j cap plus T by 2 into I cap equals 0. Now multiplying both sides with minus 1, this can be written as 0.5 I cap plus 1.5 j cap cross T by 2 I cap plus NB minus W by 4 into j cap equals 0. Now, taking the cross product, we get I cross I becomes 0, therefore 0. Then I cross j becomes k. So, plus NB minus W divided by 4 into k cap into 0.5. Here there is 0.5, so this into 0.5. Then 1.5 j cap cross T by 2 I cap means minus 1.5 by 2 T k cap. K cross I means minus k cap. Then minus 0 equals 0. So we see that NB minus W by 4 minus 0.75 T equals 0. NB minus W by 4 into, here there is a 0.5. So 0.5 into NB minus W by 4 minus 0.75 T equals 0. Now multiplying with 2, we get NB minus W by 4 minus 1.5 T equals 0, or NB minus 1.5 T equals W divided by 4 equals 392 divided by 4, or it is 98. Thus we get NB minus 1.5 T equals 98. This is relation 1. Now let us take the rotation equilibrium of the ladder AC. Taking moments about A, we can write AC vector cross NC vector plus AE vector cross T2 vector equals 0. Now let AC vector equals C vector. then this is equal to C vector means 0.5 into I cap minus 1.5 into j cap, and also A vector is clearly half of a C vector, that means it is C vector by 2. So the above relation becomes C vector cross NC vector plus C vector by 2 cross T2 vector equals 0. That means C vector cross NC vector plus T2 vector by 2 equals 0. That means 0.5 I cap minus 1.5 j cap cross NC vector means NC into j cap plus 1 by 2 into T2 vector means T into minus I cap equals 0. Now we can take the cross products. So 0.5 I cap into NC j cap means 0.5 NC into j cross I means k. So that into k cap. Now I cross I becomes 0. Now minus 1.5 j cap into NC j cap means 0. Then minus into minus plus 1.5 t by 2 into j cross I means minus k. So minus k cap equals 0. That means 0.5 NC minus 1.5 by 2 t equals 0. Multiplying both the two, we get NC minus 1.5 t equals 0. Let this be equation 2. Now relation 1 minus relation 2 implies that NB minus NC equals minus 1.5 t and minus 1.5 t gets cancelled. Therefore 98 minus 0, right hand side becomes 98 minus 0 or 98. Let this be equation 3. Now we can equate the magnitudes of the total upward force and downward force. The total upward force is NB plus NC. So we can equate the magnitude of the total upward force, that means NB plus NC. This is numerically equal to the only downward force, that is the weight W. So that's equal to 392. This is relation 4. Now 3 plus 4 gives that 2NB equals 98 plus 392 means 490. This is 490. From that we get NB as 245 newtons. Therefore 4 becomes NC equals 392 minus 245 equals 147 newtons. Now substituting the value of NC in equation 2. Equation 2 becomes 147 minus 1.5 t equals 0, or t equals 147 divided by 1.5. This is found to be 98 newtons. Okay.